No, we are going to have 5 presentations on the draft GMPEs. I'm very proud that we have 5 models out of 5 models developed, and our commitment, contractual commitment, was minimum 3, and now we are delivering 5, which is great. So Norm is going to talk about the first one, then we'll go with the Bohr and others models, and 5 presentations. Norm.
Good afternoon. It's usually good to have a name that starts with A. Where is the microphone? Oh, I'm sorry. Having a name that starts with A, I'm usually in the front, which is good. Today, that's not so good. So I was the last one to finish, and just finishing up getting the model numbers out early this morning. So I'll be shorter probably than the others. Let me tell you what we did on the. I'm going to tell you the philosophy that we use in doing the modeling, and then I'll show you example results, and you can tell where things are heading. The data set. Generally, before Walt and I, our approach had been the more the merrier. You know, more data is better, and we lived with some instead of being very particular about getting the highest quality data, we went for volume, okay, and sort of make up with it with statistics. This time, the Italian and Wenchuan aftershocks are a big set of data. There's probably 80 or 90 earthquakes in those 2 sets, and I still can't make good sense out of them. And so I put down here, I've excluded them right now. We're going to try to bring them back, but I'm still not convinced the metadata are correct. We get some unusual scaling that comes out of those. So right now, those are not in there. All the other class 2 events that Katie talked about are included with the tapering of the effect that she showed you, so that we went out to that delta centroid joiner bore distance of 15 kilometers was the edge of a class 2 event having a lower than average median ground motion. I've gone back and forth on the Wenchuan earthquake. It's in there now because I, in the end, felt like it's a big earthquake. I got to include it. But the Wenchuan spectral shape is very similar to the spectral shape of all of its aftershocks in terms of its deviation from our standard model. So it's enriched in high frequencies, and it's really weak and low in long periods. The 70 or 80 aftershocks show the same kind of behavior. So I think it really suffers from a regional side effect. But right now, it's just thrown in there as everything else. My model. So this is the easy part, right? This is the simple part of the equation. There are a whole bunch of pictures. So if you're familiar with our models before, I will say they are not getting simpler in general. And anyone who wants to try to tell me how to simplify this, I'm happy to do it. If you can tell me which one of these parameters to take out. We have a basic model. This is the regular old GMPs that you've seen with magnitude and distance. We have stylofaulting, a reverse and then normal factors. The class 1 factor that you just talked about, how that's tapered. There's a soil factor, nonlinear site response, using the models that Ronnie talked about. Hanging wall. This is the big problem. It's a large effect. It matters. Okay, hanging wall effects are significant in close where we care about design ground motions, and you need to have those effects taper smoothly or very smoothly with all of these parameters. So that's probably a whole page of equations just to tell you how we're modeling the hanging wall effect. The depth at top of rupture is really becoming a stronger effect than what I've seen before. And then there's a Q term here, the large distance term, and then a soil depth term. So any one of those you want me to get rid of, I'm glad to listen if you can tell me what we're going to do to move forward. The base model, really simple, okay? This is your easiest model. We used to have 2 pieces here, so I don't expect you to pay attention, but you have a constant, and I've got deltas in here because I'm going to regionalize these models. We're no longer saying the whole world is the same, okay? So there's going to be some differences. But basically, you got a linear magnitude term, a quadratic magnitude term. Those have to be there, right? And then I'm going to multiply by my distance, and I'm going to have a magnitude-dependent slope. Simple. But I have to have a break in the scaling. Before we had the break at around 6.7. Now I've moved it back to 6.3. And I'll tell you in a minute why. But then before we had 2 breaks, or just 1 break here, then when you had the problem that Yusuf talked about, we did not fit small magnitude data. We overestimated it significantly. Why that matters is small magnitude data can be informative to you on the attenuation properties in a region. And it can inform you on what's happening in the larger magnitudes. But you can't inform you if you're using models that were never intended to be used or predict those values. So we have another breakpoint. And this is at 6.3, and the other one is at 4.5. You really cannot model these data without those kinds of breaks. Hanging wall model. So 5 tapers. I'm not going to go through all the equations on the tapers for you because those are terrible, but taper magnitude, dip, and top of rupture, distance over the rupture. So Jennifer talked about these, and then distance off the rupture. So I use Jennifer's models for magnitude dip and the distance over the rupture. The reason for this is we have 5 earthquakes in the entire data set where we have close-in data on both the footwall and the hanging wall. If you don't have data on both sides, you suck this effect up into some other parameter. It's too well correlated. So you cannot do that. So you can't get the scaling for all of these things. We know it should taper with magnitude. It should change with dip. It should smoothly with distance. The depth of the rupture effect, I basically just set that model. Okay, there's really very little to go on. So that it's at 30% reduced at 5 kilometers and no effect below 10 kilometers. I have nothing to go on besides that. And the distance effect off the edge of the rupture, Jennifer mentioned, the data all fall off faster than what the numerical simulation showed, and so I have tapered that off faster. Top of rupture. This is really becoming, in my model, or our model here, a stronger parameter. If you fit the regression with just your base model and then start looking at everything else, the strongest parameter left is the top of rupture, by far. Okay, it really starts to dominate. I've used top of rupture and not hypocentral depth. The reason is, as a person that runs hazard, I'm trying to make our life easier. Okay, if we put in hypocentral depth, that's another aleatory variable. We've got to add another loop inside the hazard. But if you will use top of rupture, we already have to compute that just to get the rupture distance. There's no extra computational burden for a top of rupture based model. There is a computational burden for a hypocentral based model. So that's the reason I've used this. I've had allowing different scaling for strike slip and disk slip. They tend to be actually very similar, other than for strike slip events that come to the surface, they're a little weaker. So there's a little stronger scaling in the top few kilometers. But this is a very strong term. The style of faulting, reverse events are defined with rake angles greater than 30. So this is rake restricted to minus 90 to 90. Normal is less than 60. Strike slip is everything else in between. So normal oblique is lumped with strike slip. Reverse oblique is lumped with reverse. These style of faulting effects you don't see in the smaller magnitude data. We now have a huge amount of it, and it is just not nearly as strong. We care about predicting larger magnitudes, so I've tapered those effects from magnitude 5 to start the taper, and then by magnitude 4 have no effective style of faulting so that those data won't mess up the model in the distance or the magnitude range that we care about. The site term, and using the nonlinear model Ronnie described, and so we're using the peninsula range model and spectral acceleration on rock as the loading level, not PGA on rock. This, again, makes life easier for you if you're on hazard because now you don't have to bring along a correlated variable, which we did before. So I am making your life simpler. You should thank us for this piece. Soil depth. So right now there's no changes. Soil depth terms are in the data set. There's quite a bit right now, but still the bulk of the stations don't have what I think are reliable depths of the soil. So I'm still using the analytical modeling techniques that we used in Abrahamson and Silva. We haven't updated that. That piece slaps on in the same way as it does now, based on the Skek 3D models and Waltz 1D models. We're going to update those, but it'll be in the exact same form. The Class 1, Class 2, because I didn't put in the Wenchuan and Italian earthquakes, which are important for Class 1, Class 2. When we did the study that Katie talked about earlier, I wasn't worried about getting the right median ground motion. I was worried about identifying differences. And so there's things you can do to get through that data that will show you the right difference between main shocks and aftershocks, or Class 1 and Class 2, I should say. But it was messing up the scaling elsewhere. So we're going to have to update this as I figure out how to deal particularly with the Wenchuan aftershocks. The large distance terms, so the modeling, as I'll explain in a second here, we fitted up to 70 kilometers first of all. That's the range we care about the most. You then simply put in a taper. Once you get beyond 70 kilometers, it scales with distance. There's another delta here. Anytime that's there, that's a regionalized parameter. So it's going to be different for California or for Japan, for example. They have a much faster scaling. And so the regionalization, there's 4 regions that I looked at. California, Taiwan, Italy really is questionable as a region if you don't have all the aftershocks in there. Japan, and then all. And all means everything put back together again. So not what's remaining, but if you're in a region that doesn't have enough data, you get thrown into the everything region. The terms to be regionalized, VS30 scaling, large distance scaling, and the constant terms. So the regression approach is trying to build a model that works well where we care about it. Large magnitude, short distances. So the first set of runs I did just with magnitudes over 5, distances within 70 kilometers, and at least 5 stations per earthquake. This helps to get a reliable event term. From that, I fixed the magnitude scaling terms that came out above magnitude 5, so those are no longer changing anymore. So no matter, then next they added in the smaller magnitude data. That was that third line of the base model then picks it up. And after that, everything that controls the ground motion within 70 kilometers is fixed. So when I go to look at the larger distance data, it can have no impact on my model at 70 kilometers or in closer other than a constant term. And I'm actually thinking of even stopping that. So it can't have any effect other than to just put in a slope at larger distances. This is what I was running this morning. It didn't work right. So right now the model works well out to 70 kilometers. Nick will show you some comparisons. It's not working right if you pushed it out to 200 kilometers. So general results, magnitude scaling, the data want oversaturation at short periods. We saw this before. It really wants it. Okay, I still won't allow it to do that. So at some point, I think we're going to be driven there, but I want to see the numerical simulations also showing me in a consistent way this kind of saturation. So if you let the data do what it wants, the scaling peaks at around 6.3, 6.4, and then the ground motion goes back down again at short distances. So that's part of the reason why I shifted the break point from 6.7 to 6.3 to help sort of smooth through that desire for oversaturation and not have too big of a misfit earlier on. You can't fit everything. If you're not going to allow the model to follow the data, you're going to have some misfits. And so that's still what we're doing. The top of rupture scaling I talked about, and I'll show you in a second. So I just have a couple examples of residuals. This is the event terms versus magnitude. So for peak acceleration, 0.2 seconds on the bottom left, 1 second, and 5 seconds. So you look at this and you say, have we missed anything? Do you have any big obvious scaling issues? And you don't. What you do see is a strong magnitude dependence in the standard deviation. You're getting larger scatter at smaller magnitudes. It's not just that you have more data points. The standard deviations back here are really around 0.3. The standard deviations back here are around 0.6. Okay, so there's a big effect of the standard deviation there. Or, excuse me, around 0.5, I think it is. But overall, we're getting a model that is not showing a bias. If anything, we're still high here. The residuals are low. That's the desire for it to oversaturate. So this is a fully saturated model, and it still wants to pull it down somewhat. The example here, just at distance, I'll just show you the one plot at 5 hertz, 0.2 seconds. This is in different distance ranges. So the magnitude 3s to 5s are in here. A whole lot of data. I mean, we are overloaded with data at this point. This is the magnitude 5s to 6s, 6s to 7s. They're still looking good. 7 to 8, you can start to see a little bit in close. Here we're actually a little bit low close in on these particular recordings. Remember, that's after the event term has been taken out. And so the oversaturation is trading off with the event terms. If you look at the top of rupture scaling, so I put this in here just to point out this is strong scaling. The way I've plotted this for you is the factor that you get with every kilometer of depth from 0 to 20 kilometers in natural log units. 0.1, way up here, would be 10%. So if you go down 5 kilometers, it's up 50%. Okay, we're not quite there yet, but this is a really strong factor at short periods. All of the new data really support this. I mean, if you start running it, again, it's the most obvious thing that comes out of your initial regression on your base model. Then it starts to go away at longer periods. Right now, I've let it go down here. I may come back and restrict it to be 0 at this point. But at long periods, there is no big scaling like this. So it's really a short period phenomenon. That means if you're worried about high-frequency motions, your buried, moderate-sized earthquakes are going to be the things that drive up the ground motion. Here's a comparison. Then I have just a couple of these with the old model and the new. So the black is the old model. The blue is the new model. So this is for magnitudes 5, 6, 7, and 8. So the 2 5s, 6s, 7, and 8s. For 760 meters per second and surface rupture. So at long periods, there's almost no change in the model. Okay, it's very similar out here in the median. This is also at 10 kilometers away. At short periods, you can see we're getting reduced small magnitude, magnitude 5s. That's what we've been talking about. That's about a factor 1.5 or so. If I had gone to magnitude 3 and had shown extrapolating the other model, it would have been factors of 5 or something like that. It's just some gigantic number here. So, but you can also see in close, we're getting stronger magnitude scaling in here than what we had before. And the peak in the spectrum is shifting at the larger magnitudes. I'm keeping the spectrum here. It's not moving over as much as what we had before. I still don't know why that's happening, and I need to work through that. Normally, we think of a model doing what the black one has, is that you peak here, and at the larger magnitudes, you're moving that over. But the data are trying to pull that back right now. If I look at the depth to top scaling, this is what we had this term in our model before. It's now just a little bit stronger in that short period range. So this is a magnitude 6 at 10 kilometer rupture distance, whether I put the depth to top at the surface, at 5, or at 10. So I'm kind of just shoving it straight down. And this is for a strike slip event. And you can see out here, we're very similar again. In the short periods, I'm moving the peak of the spectrum over a little bit. And a little stronger depth scaling than before. But at PJ, it's about the same as what we had previously. If we look at the effect of the hanging wall, so hanging wall is a big deal. Factors, this is a magnitude 745-degree dip, and what I've shown you is the dashed lines are hanging wall, the solid lines are footwall sites. This is the new model versus the old model. This is in close over these events. We're getting a large increase here at the short periods. So this is back to, this is not The hanging wall effect is from a solid line to a dashed line. Okay, so those are actually comparable sizes of their hanging wall effect, but our overall model is already on the footwall increased more at the high frequencies or short periods. The standard deviation model, as I said before, is strongly magnitude dependent, especially with all these little earthquakes that you put in or that are in this data set. This is total sigma, so this is a combination of the within event and between event terms. The within event term dominates by far. It is a much bigger piece. You can see here, magnitude 3s are way up here. Sigmas of 0.9. Fortunately, we don't care much about ground motions from magnitude 3s. Okay, but you can't use those, in other words, to inform you of the standard deviation. This is an issue in the eastern United States. What's our standard deviation there? Well, we can get it from magnitude 3s, but that doesn't tell us what we want to use for larger magnitudes. And so then this comes down at longer periods. There's actually not as much variability at longer periods from the small magnitudes. This is, so then the solid blue line is, this is a magnitude 5. And here is a magnitude 7. So for the big earthquakes, the trend is increasing sigma with period. But for the smaller earthquakes, the magnitude 5, it's almost flat. And the magnitude 3s, it goes the other way around. Comparison, this is what we had in the 2008 model for magnitude 5s. And I plotted 3s here, but it's the same, right? We didn't have any 3s in our model. Okay, the style of faulting effect, just to show you what that looks like. So this is a magnitude 7, 10-kilometer rupture distance on the footwall, so we don't have any hanging wall effects in there, just showing you strike slip is the heavy dashed line, the long dashed lines, normal is short dashed lines, and reverse is here. So in our previous model, there was very weak dependence on the style of faulting. We had almost nothing there at that time, and part of it is we thought we were taking up most of what was seen as style of faulting effects previously with depth of rupture effects. Now we can still see it. Okay, we have enough data to sort of be able to pull these things out, where we have data over a broad range of depths and a broad range of style of faulting. We still have very few normal events. So the normal number here is very poorly constrained. The data, the factors for normal varied from minus 0.1 to minus 0.5, and I just put an average of minus 0.3 for all periods because I don't believe it yet, or I don't think it's reliable to have that period dependence in there. But here would be my normal, my strike slip. So this is nominally 10 to 15% here. And then up to reverse, and you can see what those factors are going to be. So potentially, we're back to having, at least in this analysis, it's suggesting we're back to having the style of faulting effect that had somewhat disappeared in our previous model. So what am I going to do to be in the next months that we have to clean this up? One, I got to fix the distance scaling and including regionalization. What I did right now was only distance scaling for the California data, and it needs to be a regionalized term. Bring in the Italian and Wenchuan class 2 events, that should say, in there. And I am determined to add kappa scaling into this model. That will be a deviation from the base model, so that if you know kappa, you'll be able to scale the model up or down and not just say, well, my VS30 is 1,000 meters per second. Whatever kappa was in our data is applied to that. So that will change for every VS30 value. There'll be a different kappa adjustment. We are going to bring along the single station sigma model. Linda should be back working on this in January, right? So that will be good. And the data are now finally here. As Yusuf said, that's another really important piece of the small magnitude data. You cannot do this problem without bringing the small magnitude data to play. And it looks to be quite predictive of what's happening in the smaller magnitude data. That's part of what we've been checking. The other part is I didn't tell you exactly what I did on the Japanese data, but the VS30 scaling at short periods in the Japanese data does not follow a nice, simple log shear wave velocity model. It has a very different slope, sometimes going the other way and up and down. What I've done right now is I've just binned it up into 7 different bins and let each bin get its own constant and ignored it in that way, but I need to build a model for that piece. And finally, we'll update the soil depth scaling. That's it.
Very good. Thank you very much, Noor. Appreciate that. So, questions for Noor? Hamid.
Noor, the figure that you showed for magnitude 3, you have a lower standard deviation for longer periods.
Yes.
I wonder why is it so?
Well, so part of it is I think the when I think about other rupture things that are happening that you can be getting, so I'm going to dance and wave my arms for you, but a more complicated rupture or finite fault rupture is going to be more dependent on direction of rupture, for example, that can start to influence the variability of this long period. But I would have thought just radiation pattern, which should be nice and systematic, would show up. But it's really clear we're getting a much smaller standard deviation at the magnitude 3s. It's at the long periods. It actually, if you let it, it crosses here and becomes less than the large magnitude standard deviation.
You've made it clear that top of rupture is very important. Some faults, sometimes they rupture to the surface and sometimes they don't, depending on just variation among that fault. Do you have any advice as to how to predict ZTOR?
Now, we don't predict. We randomize a parameter and run through all of the cases with their different probabilities. The difficulty you have is, what do you do on a deterministic analysis? Because closer doesn't mean bigger ground motion. That's the issue that is the difficulty here. And the probabilistic analysis, it's easy. In fact, we're set up to do exactly that.
Well, I was speaking from a deterministic point of view, of course.
So give it up.
There was another question? There was another? No.
So follow up from Vladimir on that, I guess, is saying that the depth of the surface, the top of rupture, is not a parameter determined by seismic network. So how much confidence do you have in what you have in the database now to come up with these effects?
Very. It's obvious. So this isn't one of those marginal things with I didn't put the points there, but if I showed you the residuals without that term, there's just a very strong slope. So we can tell the difference between even magnitude 5s at 20 kilometers or 3 kilometers depth. Okay, I believe those numbers. And really, the top of rupture for any of the small events is essentially the hypocentral distance minus a little bit. Okay, it's providing you almost the same information. Where it's really different is the large magnitudes.
One more questions? I saw.
This also helps me oversaturate the models, right? Because the larger magnitudes want to rupture to the surface, so they get this reduction.
Yeah, the point, I guess, is more when you parameterize that, you can see the effect, but how you parameterize it depending on how the impact of how you estimate.
Correct. But so if the estimates are good to a few kilometers, that's plenty. Okay. We're looking at a difference between 3 kilometer or surface ruptures and 10 to 20 kilometer depths. So I don't think that's our biggest problem.
Could you explain again how you're determining the top of rupture? It seems like in some cases if it ruptures down dip, it's the hypocentral distance. And I'm not understanding if you're using the location of the aftershocks as the top of rupture? No, we're using,
for big events, we're using finite fault inversions for the slip model to define the rupture plane. And then we take the top of the rupture plane.
Very good.